All right. I think we can go ahead and get started, Robin.
Okay.
And actually, Jacob or Ryan, did you want to do a quick like, hey, we're Ultrametric, our awesome, the meetup's awesome sponsors, just
Yeah,
before Robin gets started?
we can real quick for sure. So I'll be extremely quick. Hi, everybody. My name is Jacob, and Ryan, who's also on the line, Ryan Robinson here.
Hello.
We work for an awesome company called Ultimetric that's headquartered in Southfield, Michigan, with a global presence, focused on digital transformation, helping big companies stay ahead of the curve with technology change. And we run a project called Collider, which is a community-facing project. We work with lots of awesome partners in the community, including Detroit Tech Watch and a bunch of other meetup groups and event organizers and hackathon organizers and such, to regularly host programming that brings together software professionals to learn, grow, connect, anything that's going to be valuable for software professionals. That's the type of stuff that we do. So we regularly host the Detroit Tech Watch meetup in our physical space that's based in downtown Detroit. Obviously, with the situation that's going on right now in the world, we're not doing physical events. We're focusing instead on virtual events, which is where you find yourself here connecting with us today. And we're really excited to continue working with Detroit Tech Watch in this format. I'll go ahead and drop the link for Collider in the chat here. But we encourage everyone to connect with us and stay in touch, because we are regularly hosting lots of awesome technology-focused programming to help you develop as a professional. So we really appreciate you working with us and look forward to learning more about the Julia programming language.
All right. Then I think I will take it
Robin,
away.
before you start,
Oh, all right.
just quick, just a couple for people who've never participated in this kind of thing before, please mute your microphone if you haven't already. Robin is going to pause at certain points in the talk so you can ask questions. So please, if you hold your questions, please. And I just want to mention before I forget, in June, we're going to have Bruce Tate, the author of 7 Languages in 7 Weeks, is going to be joining us. I don't remember the topic of his talk, but I am very much looking forward to it because I've seen Bruce speak before, and just like Robin, he's a terrific speaker and he's got a lot of interesting things to say. So, all right, enough of my advertising. Go ahead, Robin. I'm sorry.
That's all right. Thanks very much. All right. Well, thank you for having me and for giving me a space to talk about my favorite programming language. If you want to follow along with all the content, I posted a URL here, and I also dropped that in the chat, so you can take a look. But otherwise, without any further ado, let's get started. So just very briefly, so you know who I am, I grew up in Michigan. I then moved to Boston to go to MIT, and I'm now at Boston Dynamics, where I have the best job in the world playing with giant humanoid robots. In my free time and in my grad school time, I helped co-found the Julia Robotics organization, which is a group of open source contributors dedicated to creating open source tools for robotics in Julia. I've also presented at some of the past Julia conferences and contributed to a bunch of different Julia projects, which you can find on my GitHub. So just to give an overview, I'm going to talk a little bit about what Julia is. And I'm going to give a hands-on tour of the language. There's no way I can possibly cover all of the things you would do. I don't expect you to come out of this being expert Julia programmers, but I do want you to have a sense of sort of what programming in the language is like. How do you organize your ideas into code in Julia? I'm then going to try to prove to you that Julia is actually fast. One of the most important selling points of this language is that it's fast enough that you don't have to rewrite all your code in C later. I'm going to try to prove that. I'll talk a little bit about some of the bonus features, things like async tasks or multiprocessing, metaprogramming, macros, fun features that you might be expecting coming from other languages. I'll also talk a little bit about what's hard to do in Julia. So what are the things that I find difficult? What are the pain points? Why might you not choose Julia for a project? And then I'll go over some of the essential tools and packages and where to go to find more. Okay, so very briefly, what is Julia? I've dropped a link to the documentation. I think for me, Julia is, it provides a lot of the benefits of a high-level language like Python. So it's a language in which it's easy to prototype ideas, write new algorithms, develop code, but it's a language where you can write reasonably readable generic code that is as fast as a fast language like C or Fortran. And that's really important because a lot of my time in grad school was spent writing code in MATLAB or Python and then having to rewrite all of that code again in C or C++ to get it to be fast enough. And then forever dealing with this two-language problem of having to move data between the two languages, construct build systems that could keep them all glued together. With Julia, you don't have that problem. You can write your code and make it fast in one environment that's pretty nice to work with. In particular, Julia is a good choice for scientific computing. And that's just because it focuses on performance. It has really good support for dense and sparse arrays, has good support for parallel computing, distributed computing, a lot of things that data scientists, optimization people, machine learning people need to do their jobs. But I also think it's just a nice environment to do programming, even if you're not doing anything you would consider scientific programming. It has a nice package ecosystem. It has a good tool for managing those packages and the environments that contain them. It has a nice type system that makes it easy to sort of use types when you need them to describe the behavior of your system, but that doesn't get in the way when you don't need them. And it has nice features like iterators, async, coroutines, and lots of other fancy things. Okay, so just a little bit of history and glance. There's going to be a lot of technical terms on this slide. If they mean nothing to you, that's totally fine. I'm sure there's at least one person in this audience for each of these terms who really cares about each of these. And so I just want to make sure I get through to them. So Julia was first released in 2012, but it didn't hit version 1 until 2018. So that meant that prior to that, it was in sort of version 0.x, and there were a lot of breaking changes. Actually, most of my grad school experience with Julia was in the era when about every year, a new version would come out and all the code would break and we would update it. But it's been in a stable 1.0 release for the last 2 years, which is great. Julia itself is completely free. The language is under the BSD license. There's some GPL libraries included. If you care, you can take them out. The way Julia works is it has a JIT compiler. So that's a just-in-time compiler. So you write your Julia code, and then as soon as you run it, it's transformed into native code at runtime. And I'll talk a little bit about what that means for Julia's performance. And if you care, we're using LLVM under the hood. Julia is garbage collected, so that means you're not calling malloc and free by yourself. It's dynamically typed, and I'll show a little bit of how we do that. And it's organized via this principle called multiple dispatch, which I'm going to go into a fair amount of detail about what that actually looks like. Okay, let's take a tour. The very basics. How do you do arithmetic? That's the kind of thing I care about. There it is. 2 + 2 is 4. That's pretty compelling. By the way, this slide deck is actually an interactive notebook. So if you have questions, I should be able to edit these talks as we go if there are more things you want to see. Julia has strings. There's hello world. That's the whole thing. They work about how you expect. It has built-in arrays that work really nicely as well. Okay, Julia functions. They look kind of like this. You declare a function. It has a name. It has a set of arguments, and it has a behavior. So that's how we say hello world. An important difference from Julia to languages like C or C++ is that in Julia, by default, a function is generic. So you can pass anything you want into it, unless you've described the type annotations of, I'm sorry, unless you've said that the function can't. So we can say hello to the array 1, 2, 3, and it works exactly as you would expect. Julia has a pretty nice type system, which allows for sort of interesting compositions of types to create new behaviors. So every value in Julia has a type. We have things like floating point and integer values. More esoteric things like the pi constant. It's not a double or a float. It's actually a built-in type called irrational, and it's parameterized on this symbol pi. And so what that means is you can actually take this constant and evaluate it into different sized floating point representations or use it in other contexts without losing any precision. Julia also has parameterized types or composed types. So the type of the array 1, 2, 3 is an array, and that array itself has parameters, and the parameters are the types of the elements of the array. So
what about
types
complex
that refer to other types? Go ahead.
What about complex numbers? Like
sure, yeah. I think it's I. Oh, sorry, I think it's M. There it is.
Oh, cool.
And so in particular, that's a complex int64. So it's using an int64 to hold the real and imaginary components. If I do this, it's now a complex of float 64.
Cool.
So you can create your own types to organize data. So here I've created a very, very simple type called person, which has a single field called name, which is itself a string. And so now that I've defined this type, I can create a value of that type called Alice. And one of the best features about Julia is that the types are extremely lightweight. So there's really no cost to using Julia types to organize your data. This is a really big difference from a language like Python, where constructing a new instance of a class is very expensive. And so in this case, I can show that the size of a person, so the amount of data required to store a person, is just the same as the amount of data required to store a pointer to a string. So there's no overhead for this type. It's just a nice way to communicate with humans and to create an API that defines what your data means. Okay. Actually, before I go into multiple dispatch, any questions on the basic stuff so far?
Yeah, Robin. I'm not familiar with the term dense versus sparse arrays. Is that
Sure.
something to cover later on, or is this something you can talk about?
No, I'm not going to cover that in much detail, but so very basically, a dense array is an array in which you actually store the value at every single point.
Okay.
So, if you have a 3x3 array, you're actually storing 9 zeros.
Gotcha.
A sparse array is an array in which you're actually only storing some subset of the entries. So in general, you assume that the entries that are not stored are 0. So if you have a 1,000,000 by 1,000,000 matrix, but you only care about 1,000 of those entries, you would want to store that as a sparse array so that you're only storing the coefficients that are actually there.
So it's sort of like laziness for arrays.
Yes.
Okay, cool.
And I can actually show you that in.
Sounds useful for game of life.
Yeah, actually, yeah. So for example, the SP zeros is sparse zeros. So this is a 3x3 matrix, but it's actually storing 0 entries. There's nothing in it. And so it's not consuming any memory to store the entries that aren't there.
Ah, very cool. Thank you.
Yep. Okay, so I want to talk a little bit about multiple dispatch. So this is how you organize code in Julia. You can create things that behave like classes, but it's not really how the language is designed. The multiple dispatch mechanism really is the central way of organizing behavior in Julia. And I've linked to a really nice talk about why this is an effective technique. Okay, so let's define a function. So I'm using the short form here, which greet of x and y just prints x greets y. This is a really nice way to talk about how any two things might greet each other. So for example, I can make two people, and I can call the greet function. And so that says, oh, Alice greets Bob. Okay, that all seems good. So there's only one greet function, and it's generic. It'll take anything we want because we didn't tell it not to. So we can say the array 123 greets the string hello world. Totally fine. But what if we want to create more interesting behavior? How do we change the way greetings happen based on who's greeting whom? Well, we can do things like organize our data into types. So Julia has abstract types, which are used to organize related types, and concrete types like this struct. So for example, a cat is a kind of animal and it has a name. And then we can define new methods for a function based on the types of its input arguments. So I'm just defining this greet again, but this time I'm saying, hey, well, if you greet and you have a person and any kind of animal, well, they do it by patting. So a person always pats an animal. So this behavior isn't part of person. It's not part of animal. It's just a verb. It's a verb that lives on its own, but it knows how to behave in the presence of a person and an animal. And we can say, well, how does a cat greet someone? Well, a cat greets any y by meowing at it. So cats, they just always meow. So,
do types have any form of subtype?
So abstract types do, concrete types don't. I can get into more detail on that at the end of the section.
Thank you.
So for example, we can create a cat. And now if we have a person greet the cat, they greet it by patting. So Alice pats Fluffy. Makes sense? And Fluffy meows at Alice. Okay, so this is all good. This is a kind of behavior we could probably create with classes in a language like Java or Python. Where it gets more interesting is that there's nothing about the first argument that's special. Julia will specialize, choose the method that's appropriate for all of the arguments. So we can create a dog. By default, a dog barks. But if a dog greets a person, they lick their face. And if a dog greets a dog, they sniff their butt, as dogs do. So we can create two dogs. So Alice greets Fido by patting. but Fido barks at Fluffy, and Fido licks Bob's face. And this is the kind of thing that in a language like C++ or Python, we might have to solve with something like a visitor pattern or a multiple visitor. In Julia, these problems don't even come up because we can explicitly say, hey, the way a dog interacts with this is by barking, and the way a dog interacts with this is by licking, or by sniffing butt. Okay, but that can get kind of confusing, right? You might forget, hey, what method of greet is being called here? How does this greeting work? So which is a really useful macro in Julia, which you pass it a function call, and it tells you, hey, that's the function that I would call for those actual inputs. So how would Alice greet Fido? Well, she would greet Fido according to this greeting of person and animal, which we defined way back. And if we were to go back to input 18, we could see that. Yeah, there it is, person and animal. And the which is sort of one example of one of the best things I think about Julia, which is the built-in tools for inspecting the behavior of Julia code. So it's really easy to ask Julia, hey, what are you about to do, and why did you do it? We can also list all of the different greetings that we have defined. So every time we defined a new version of greet, we created a new method. So we defined how to greet a dog greets a dog, how a dog greets a person an animal. Remember, animal's an abstract type. That's fine. We can use abstract or concrete types when we define them. Here's how a cat greets anything, and so on. Any other questions on multiple dispatch?
So when you, like you said, you could greet, like one of the greets was person and animal, and then cat is derived from animal. So is automatically go to the most specific greet then, right?
Exactly, yeah. So it will always
Okay.
choose the most specific. Now, you can create situations in which there's no most specific answer. You might have a method of greeting for any with animal. I won't get this right off the top of my head. But it's easy to construct situations where there are two choices that could be considered equally specific. And in that case, the language will throw an appropriate error saying, no, there's no, this is an ambiguous call. And the solution is you need to define a more specific way to resolve that ambiguity.
Okay, that makes sense. Thank you.
Can an abstract class have whatever the relationship is with another abstract class?
Yes, definitely.
Like
so we can do
dangerous animal, dangerous cat.
Absolutely. So there it is. So there's a tiger, which is a kind of dangerous animal, which is itself a kind of animal. So if we have greet Alice of a tiger, then she's going to pat him because tiger is a dangerous animal is an animal, and we know how person greets animal.
If you get your hand back, you're lucky.
That's right, yeah. Okay, so modules are the way you organize code in namespaces in Julia. I'm not going to go into a lot of detail on this. I think it's just important to know, yep, Julia has namespaces. It's a good idea. It's important. Here they are. If you want to learn more, there's a whole section in the manual about it. We have a command called using, which brings any symbols which were labeled with export into the current namespace. So this is kind of like from my useful module import hello in Python. Okay. So I want to talk a little bit about packages. So one of the best features of Julia is its built-in package manager, which works kind of like pip in Python to handle installing packages. But it also helps manage the environments that those packages live in so that you don't have 8 different projects that all require conflicting versions of some dependency. So a package environment is a way of representing a single set of installed packages. You activate an environment with this package.activate function. And so I've actually made an environment for this talk. And if you check out the source code at the link that I provided at the beginning, you can see the project that I created that includes all the dependencies for this talk. So what does that look like? So once we've activated a package, we can install activated an environment, we can install new packages into it. So in this case, I'm installing the colors package, which is a nice package for working with colors and images in Julia. And it will only be installed into that environment, so it's not going to break anything else that I'm doing on my system. And if you want to see the description of the environment, we can look at this project.toml file. So the project.toml is just a list of all of the dependencies of this current project. So these are just names of packages. The big, long, unreadable mess is just a unique identifier that resolves any ambiguity of packages that might have the same name. I've also sneakily shown off another feature of Julia here, which is how easy it is to run external commands. So you might recognize cat, that's a Linux command line program. So the backticks in Julia create a command object, which is a way of representing an external command you might want to run on your system. And then the run function runs it. So this would be kind of like os.system in Python. But the command objects in Julia have some really nice features, like they're very smart about not accidentally introducing quotation errors. So similar to something like node.lock in Node.js, Julia also produces a manifest file, which is a complete list of all of the packages that are currently installed in an environment. It's not something you would typically look at or read by hand, but it's something you could hand to another person so that they could exactly reproduce your environment. Okay, so let's use an example of using an external package to do something fun. So I'm going to show off a little of the features of the colors.jl package. So I'm going to load this package with using. I'm going to say using colors, and I just want the RGB type. So that's the only thing I need right now. I'm just going to bring that into scope. And here's RGB. So that's RGB, red, green, blue, and there it is. It's red. That's nice. And that works because the RGB type actually knows how to print itself out as a colored div in Jupyter, which is what I'm doing right now. If that's too fancy, you can also just print it as a string, and there it is. Okay, so I was talking earlier about how Julia arrays are really nice, and one of the nice things is that they're parameterized. So an array in Julia knows the type of its elements. So for example, we can create an array of color. So this is an RGB, and I've used a list comprehension, which is something you might recognize if you're familiar with list comprehensions in Python. And I've just created, I and j for a range of red and a range of green values. And so I've created sort of a nice color spectrum from black to red, black to green, and all the way to yellow. And so what is that? Well, that thing I've just created, that's just an array of RGBs where each component of the RGB is itself a float 64. The 2 means it has 2 dimensions because it's a matrix. Okay, well, that's a normal array, so we can index into that. So there's 1 pixel of that array. Here's a row. Looking at the first row, all the columns. And we can do even fancier things with this. Like at this point, we sort of accidentally taken this package that just knows how to represent individual color pixels and turned it into a very simple image processing library. For example, let's say we want to pull out the red channel. So let's get a few more functions from this colors package. We'll get the red, green, and blue functions. If you're ever confused about what a function does, we have this question mark operator, which lets you ask, hey, what does the red function do? And it says, oh, it returns the red component of a color. Okay, that seems useful. So how does that work? So we can ask for what is the red component of the first row, first column element of our image? It's 0. Okay, cool. Well, what if we want to know the red channel of all of the pixels? Can we find out without having to write a loop or do something more complicated? So Julia has this really nice syntax called broadcasting. So by calling f dot of x, it applies the function f to each element of x. And that actually works for any number of arguments of any dimension as long as those dimensions are compatible. So for example, here's red dot of c. So that says the red of every element of c. So we get a matrix back showing the red component of every element. But looking at numbers, that's not a great way to represent visual data. So let's try something fancier. Let's actually render that as an image. I'm going to grab one more type called gray, and I'm going to do gray dot of red dot of C. So this says, for each element in C, get its red value, and then draw that as a gray pixel. And so this is an image of the same dimension, but it's just showing the gray, a grayscale version of the red channel. And that's exactly what we wanted. And it's actually even fancier than you might imagine, because Julia actually guarantees that when you do gray dot of red dot of x, it's only going to do exactly one loop. And that means that it avoids allocating a bunch of memory for intermediate results. And generally, it means you get answers faster. This is an important advantage over a language like Python with Numpy, which really doesn't have a mechanism for doing this efficiently. Okay, so we talked a little bit about packages. Any questions on packages?
I'm going to ask you lots of questions, Robin.
Go for it.
I was going to say, I noticed you talked about doc strings. Did you guys pull over that feature from Python, the doc test stuff?
That's a good question. I actually don't know what the origin of the doc strings are. I can show you how to create one. So all you do is you attach a string right before the definition of a function.
Okay.
So we've added this documentation to the function, and then we look it up, and there it is.
Okay.
Yeah, I don't know the origin of the particular choice of syntax. There is a doc test system built into Documenter, which is a package for taking Julia code and generating HTML documentation, but I don't have a lot of experience with it.
That's what I was thinking. The doc test, because they borrowed it in Elixir too, and I'm a big fan of Elixir.
Yeah,
And,
no, it's a really good idea.
Yeah, it really is, because then you can put documentation right in your source and make sure that your documentation always matches, you know, that your documentation doesn't get out of date. Here's an example, and I can check it against the source and make sure it still works.
Exactly.
Yeah. Cool.
All right, let's talk about Julia as fast. So I claimed it has performance on par with C. That's a pretty big claim. So I'd like to prove it with exactly one example. And that'll be my conclusive anecdote that will totally show this. All right, so I'm going to implement sum, just adding up a vector. And I'm going to implement it in Julia and in C and in Python and try to compare the results. So let's start with Julia. So here's a function that sums up a vector x. So I'm going to grab an appropriate kind of 0. So x might be a vector of integers or floats or something more interesting. So whatever those are, just give me the right kind of 0. And then for each element in that vector, I'm going to add that element to the result and return the result. I hope that's a fairly uncontroversial implementation of summation. I'll leave that up just for a sec because this is a new language for everybody. Okay. So let's benchmark this. I'm going to create some data. So random float 64s, and I want 10 to the 7th of them. So 10 million numbers, just to get a big sample of something kind of large. Okay, so we're going to measure the performance of this tool, of this function, using benchmark tools. So benchmark tools is another external Julia package. If you look at the environment that we defined, I've already installed it here for convenience. And it provides this really nice tool called benchmark. So benchmark takes a function and some inputs. This $sign is part of the benchmarking tool. And it tells you how fast that function runs. And it does it by running it a bunch of times to try to get a statistically meaningful representation of the function's performance. So in this case, you can see we actually ran that function 414 times to get an estimate that it takes about 11.9 milliseconds. It also gave us a bunch of other data. So the minimum, the median, the mean, the maximum time. For this, we really only care about the minimum. And that's true because in benchmarking, the noise is typically only positive. And so we can ignore the noise by looking at the minimum time. And so since I only care about the minimum right now, I'm going to use b time, which is just a shorthand for benchmark time. And that just gives us the same thing, about 11.7 milliseconds. Okay, so I don't know, 11.7 milliseconds, is that fast? Well, we got to compare it against something. So let's try this in C. So one of the nice features about Julia is that it's really easy to call into C shared libraries. So it's really easy to integrate with C code that you may already have. So for example, I'm going to write a function here called C compare. This takes two Julia strings, and then it compares them, but it actually compares them by calling strcmp. So we're actually going to call into string comparison from libc. So just using whatever libc I have installed on my system already, we can call directly into it with no additional overhead. All we have to do is tell it, oh, well, that function returns an int, and it takes a char star and a char star. And Julia has this useful shorthand C string, which just says, hey, this is going to be a C function, and it's going to expect a char star. Okay, so how do we use that? Well, we don't have to do anything. There's no build process. There's no linking step. All we do is call it. So C compare of hello and hello. Those are two regular Julia strings, and it returns 0, which says, yep, those strings are identical. We didn't have to do anything else. Now we're talking directly to C. Okay, so let's make sure that that doesn't have a bunch of overhead. We can actually benchmark comparing hello and hello using libc, and that takes 8.7 nanoseconds. That includes the actual comparison. So the overhead of talking to C itself is very, very low, which is really cool. Okay, so let's implement sum in C. I don't want to leave this presentation, so I'm going to do it directly in Julia without leaving Julia, just to be fancy. So here's a C function that implements sum. It takes a number of elements, double star, so a pointer to a collection of doubles, and adds them all up. Should be fairly uncontroversial also. Okay, so just a little bit of overhead. I got to generate a name for a shared library. So here's a random temporary .so file. Let's compile it. Well, I said that we could talk to external commands in Julia. One of the nice things you can actually do is open those commands as if they were a file or a buffer and write directly into them. So I'm going to open GCC as an external command and write my C code into it, and that will produce a shared library. And then I'm just going to write a little Julia function that takes an array and calls that C sum function from my C library and returns its sum using C. Okay, but I said I was going to measure the performance, so let's time it. So this is benchmarking the C sum function on that data, and it turns out that takes about 11.3 milliseconds. Well, how does that compare? I've already forgotten what the Julia results are, so let's compare them with a plot. I'm going to use the plots package in Julia. So here's what the timing was in Julia, and here's what it was in C. And you can see the C came out a little bit faster, right? 11.3 versus 11.7 milliseconds. I'll tell you that I've run this a bunch of times, and which one is faster by 0.1 milliseconds flips back and forth each time I run it. So it's fair to say that the performance of Julia and the C functions are basically the same in this case. So that's pretty good. Our naive Julia code, we didn't really do anything other than just write regular Julia code. It's as fast as regular C code. We didn't have to drop into another language. We didn't have to do anything obscure. We didn't have to create a build system. We got a really nice, fast implementation of sum. But I bet it's not fast enough. There's got to be a way to go faster, right? So Julia has a built-in sum function. So is that faster? Yeah, actually. So Julia sum, the one that comes with the language, actually comes in at about half that time. It's twice as fast. So that's cool, right? It's faster than C, but it sort of raises a question like, why? How is it doing something that my user code isn't going to have access to, right? Is it using some built-in magic that I can't rely on? No, actually, it turns out it's really easy to make our function that fast. We're going to add a couple of annotations. So I'm going to say that I use the inbounds macro, which says, within the context of this expression, please don't do any bounds checking. So by default, Julia is careful about not reading past the end of an array. So if I do 1, 2, 3, and I try to do x of 5, it's going to throw a bounds error. But checking that, right, checking that 5 is outside of bounds, imposes a little bit of cost. And so Julia tries to be safe by default, but it allows you, if you really care about performance, and you know that you're not doing anything out of bounds, to turn off that checking. So that's what the inbounds does. And then at SIMD says, actually, you're allowed to even do some additional optimizations. Maybe even rearrange the order of the loop a little bit to fit better into vector instructions. So this uses the instructions that are present on modern CPUs to actually compute multiple elements of this result at the same time. So by doing that, we created a function, so myFastSum, which returns the sum of the same value, right, in about 5.3 milliseconds. And so if we compare that, we can see that our fast summation, which was just a couple of small modifications on our naive version, is now just as fast as the built-in one in Julia and twice as fast as our naive function in C. We could also go through and add SIMD or AVX instructions to the C function, but I would bet it would be a little bit more work than just the inbounds and SIMD decorators. And the nice thing is that the fast sum is still totally generic, right? It doesn't just work for doubles, it works for anything we want. So we can add an int and a double and an irrational and get a result that makes sense. Okay, so just for reference, I want to compare this with Python. I showed how you could call C code from Julia. It's actually also really easy to call Python code, which is really nice because almost everyone at least in the scientific world, has some body of Python code that they depend on for what they're doing. And so not having to totally give that up, but being able to call useful Python code from Julia is really nice. So the PyCall package provides an interface for talking from Julia to Python. So for example, we can import the math module from Python itself. And so this is computing sine, but doing it literally in Python with all of the appropriate conversions. So it takes a Julia number, hands it to Python, calls sine, and hands you the result back in a way that you can integrate in the rest of your Julia code. So we can implement sum in Python. So here's my version of sum that I wrote in Python, embedded in Julia. We're just going to initialize the result, iterate over the elements, and add them up. And we can get a reference to that Python object as a Python function, or as a Julia-compatible function called PySum. Okay, so what that means is PySum will now let us actually add up a vector of elements, but do it in Python. Just to make sure that I did this right, we can check that the PySum of the data and the CSum of the data and the Julia built-in sum and my sum and my fast sum, and they all give approximately the same result. They actually won't be exactly equal because some versions of these will exploit SIMD or pairwise addition to achieve very slightly different answers due to floating point rounding, but they'll all give approximately the same answer. Okay, so let's time that. So timing the Python sum, it takes 724 milliseconds, which in context is a lot more, right? It's more than 100 times the time of our fast Julia implementation. And that's really what we mean when we say that Python is a slow language. And like, I love Python. I think there's a lot to love about it. But when we say it's a slow language, what we mean is, if you write code that actually executes a lot of instructions in Python in a loop, it will be slow because every single thing you do in Python has overhead. Adding two numbers has overhead because Python has to, every time you do it, check, hey, how do I add numbers? Okay, cool. Well, where am I putting them? How do I allocate memory for the result? And so that means that if you want to write fast code in Python, you do it by calling something like Numpy, where you pack all your data into a vector and then let Numpy iterate over it in code that was written in a faster language like C. But in Julia, we don't have to do that. If you want to write a loop, just write a loop and it will be fast. In fact, it will be as fast as whatever loop you would write in C. But this is kind of a straw man. Like nobody would sum up a vector of numbers in Python by iterating them over in a loop. You would use NumPy, like numpy.sum. And it's great. I mean, NumPy is a really amazing tool, but it has some caveats. So NumPy is really only efficient for a predetermined set of numeric types. So if your data are made up of vectors or matrices or arrays of floats or doubles or ints, great. NumPy totally has you covered. But if your data aren't made up of that, or if you want to do things that aren't covered by the sets of functions and types that NumPy exports, it's really hard to write efficient code without having to switch to a new language like C and a new build system and a new environment. And if you don't want to do that, you can just write it in Julia. And so what do I mean about generics? Well, all right, I'm going to make a point type. So this is a point. It has an X and Y coordinate. And the T syntax here means for any T. So you could have a point of ints or a point of floats or a point of complexes. And all I'm saying is, well, whatever it is, the X and the Y, they're the same. I can say, here's how you make a 0. So this is how you make a 0 point. Well, you make it by giving it a 0x and a 0y. And then I can say, hey, here's how you add. So I'm going to implement the plus for points. And you add the x components, you add the y components. And then I can make 10 to the 7th points. Well, let's add those up. So we can use the same function, myFastSum, and we can add up 10 million points. And it takes 15 milliseconds. Which is pretty cool because remember, it took 5 milliseconds to add 10 million numbers. And each point is 2 numbers. So the sort of the best possible experience you could expect for adding up 10 million points would be roughly 10 milliseconds. And so what this means is we created a nice generic implementation that's still fast when called with a type that we'd never seen before, right? The overhead of the existence of this point type is close to 0. And I suspect with a little bit of SIMD tweaking, we could probably get it down to exactly 0. I'm actually surprised that it takes more than 10 milliseconds to do this. But 15 is still pretty good, given that we have this nice implementation that's totally generic. And in case you really care, you can actually look at what happens when you do this. One of the nice introspection tools in Julia is called Code Native. It lets you take a function call and inspect the actual assembly that is generated for that function call. This is not, I don't speak Intel assembly anymore, so this means very little to me. But there are people who care about this a lot, and being able to inspect the code as you develop it is really nice. Okay, any questions about Julia performance before I move on? Oh, there was a question about how do we know we're using a specific environment? It's actually hard for me to show in this notebook, but Julia has a special built-in package prompt, which you can activate at the terminal, and that prompt shows you the name of the active environment. It's kind of like a lot of people have bash extensions that show you what Git branch you're on. It's very similar. All right, let's move on to some bonus features. So one thing that's very common to do in languages like Julia or Python is asynchronous operations. So you might want to talk to a web server a bunch of times, or write a bunch of files, do a bunch of things that aren't necessarily computationally intensive, but might each take a bunch of time because you're waiting for some result. So Julia has a nice solution for this called @async. So async says, don't do this, do this eventually. Create a task which will go off and do the result of this operation, but do it in the background. It works a lot like async and await in Python or in JavaScript. And so you can see what I've done here is I'm iterating from 1 to 5. And each iteration, I'm starting a request to this fake API service that I found. And then whenever I get its result, I'm going to print back the status. As you can see, we're going to send out those requests 1, 2, 3, 4, 5. And they come back whenever. Each of those tasks can finish whenever their website happens to respond. We're not blocked waiting for them to respond. And I bet if we run this again, we'll get them back in a different order. So this time we got 1, 2, 3, 5, 4. And that's fine. If you want to use, if you want to ensure that you wait for all of them to finish, there's a macro called @sync, which will block until all of the asyncs inside of it have finished. Julia also has channels for scheduling operations between these sort of lightweight tasks. So that's a good choice if you're doing something that's not computationally intensive, but just might involve a lot of waiting. Julia also has multi-threading. And I'm not going to have a lot of time to go into this, but I would encourage you to check out this really cool blog entry on the parallel task runtime. And just to give you a teaser of what that lets you do is, for example, here's the Fibonacci sequence implemented by, at every single call, spawning a new parallel task to compute Fibonacci of n-2, and then combining its result with Fibonacci of n-1. This is still a bad way to write Fibonacci, right? You're doing vastly more work than you actually need to. But the neat thing is just how easy it is to make this fully parallel, and in a way that doesn't totally oversubscribe your processors. So you're not going to spend time thrashing around between thousands of different tasks. But yeah, not enough time to go into this, but please check out the blog for more details. One nice thing about Julia compared to C++ is that nothing is ever copied unless you ask it to. And so a very common idiom in Julia is to do work in place. So this is a function called invert. I've added the exclamation point. That's just a signal to the user. It just means, hey, I'm going to modify whatever you pass in, so be aware. And I'm going to invert each element. Okay, so we use that. We might create a vector and then invert it. And now if we look at that vector, now it's been inverted. So we didn't need to do anything. We didn't need to mark this as a reference or a pointer argument. That's just how all arguments in Julia work. And we can see if we time it that inverting that vector takes very little time and allocates no memory at all, because all of its work was done in place. That's really important for data science, where you have huge amounts of data. It's also important in things like robotics, where you want to avoid memory allocation because it might be slow. One of the nice features about Julia is that anything can be a value. So there's no special rules. It's not hard to pass functions or types or anything into a new function. So a function is a value. So here's MapReduce, which is the classic example of functional programming. So we're going to map an operator over an array, combine it by a reduction starting from some initial value. Super duper simple. It should look almost exactly like the version of sum that we implemented before. Okay, so how does that work? So here's the sign of each element combined by plus starting at 0. I think that's probably right. I can't off the top of my head tell you what the reduction of plus over the sign of 1, 2, 3, 4 is, but I think that's about right. Okay, so well, we can implement sum pretty easily in terms of MapReduce, which is kind of nice. So sum is just a MapReduce of the identity combined by the plus over the vector starting at whatever the appropriate 0 is. So this is all well and good, but how does it perform, right? Are we going to pay a big price for doing this sort of higher order functional programming? And the answer is no, we pay no price at all. So if we look at the timing for this fancy sum, which uses MapReduce, on higher order functions, it's exactly the same performance as our original handwritten sum, 11 point something milliseconds. And I'm pretty confident that if we wanted to get that all the way down to 5 milliseconds, the same inbounds SIMD tricks would be enough to get you there. Okay, so we can pass functions around, and we can call functions that are made up of functions calling functions, and everything just works, and it still performs well. Well, types, those are also values. There's no reason you can't pass types around. And in fact, we do this all the time. So for example, here's a function that's going to give you an empty matrix of some type with a given number of rows and columns. And so we can ask for an empty matrix of ints or an empty matrix of that point type that we defined earlier in the talk, and everything just works. This is the kind of thing that's weirdly challenging to do in C++, which has very complicated parsing rules about passing types or templated functions around. Even Julia expressions themselves are values. So Julia's inherited a lot of its design actually from Lisp. And one of the ways in which that shows is the fact that the language itself is represented in data structures of the language. What do I mean by that? Okay, well, so I can make a representation not of 3, but of the expression 1 plus 2. And so I can look at that. Well, it has a head, so it's a call. Okay, so this is going to call some kind of function. What's it doing? Well, it has arguments, so it's going to call the plus function on 1 and 2. And if you're familiar with Lisp, this should sort of feel familiar. This is starting to look like basically just a regular Lisp expression. And so since expressions are values, we can just write functions that operate on those values. So I make a lot of sign errors because I'm a roboticist. So maybe I want to be able to switch all of my plus calls to minus calls, because maybe that'll fix all my sign errors, right? So we can write a function that operates on an expression and says, oh, hey, is this a call? And is it a call to some kind of plus? Well, if so, just swap it to a minus. And also do that recursively for all of the arguments. And so we can manipulate this expression without doing any string manipulation. We don't have to split the tokens into their components. We don't have to get lost producing things that don't make any sense. We're just operating on an expression as a data structure. So for example, here's 1 plus 2 times 3 plus 4 times square root of 2. We can switch that to subtraction. And now we have 1 minus 2 times 3 minus 4 times square root of 2. And maybe that fixed whatever was wrong with our robot. Probably not, though. Okay, so well, if an expression is just a value, then macros are essentially just Julia functions that operate on those expressions. So for example, I want to add more cats. So I want to take an expression, and I want to find every string literal in that expression, and I want to make it cat, because cats are better than whatever string you had in there. So I'm going to index over the arguments of the expression and say, hey, is this a string? Like, did someone put a literal string in this expression? If so, just make it cat. Okay, so we call macros in Julia with this at prefix. And you've seen me use this in a bunch of other places. So I showed you at which, at inbounds, at SIMD, at benchmark, at btime. Those are all regular macros. They're written in Julia. The syntax is exactly the same as writing a function, and they just operate on expressions. So for example, at more cats of print line hello world, well, that prints cat. But if it's confusing why that's the case, we have a macro called macro expand, which says, hey, given this macro, what does it do? Okay, well, macro expanding more cats print line hello world, well, it's turned hello world into cat. So it's actually just print line cat. And you can always do this. So if we wanted to see how would you benchmark, we can see how benchmarking actually works in Julia. It's a little complicated because it actually does a bunch of work to warm up the function, tune the parameters of the benchmarking, run the result. But you can inspect this as deeply as you want, which is really important for debugging and development. All right, so at more cats is a bad macro, not very useful, but there are a lot of actually useful ones in Julia. So at show prints out a value and the variable that's bound to, which is something you can't do with a function. We have at time and at btime, which measure timing. One of my favorites is show progress, which actually turns a for loop into a live updating progress bar. And it does that by just running the loop one time and estimating the amount of time left by knowing the number of iterations of the loop. Okay, a little bit about what's hard to do in Julia. I won't have time to cover it because lots of things are hard in every language. There's a really good post on Discourse about what the compiler team is working on right now. And there's a really good talk by Jeff Bezinson, who's one of the authors of Julia, about what he sort of thinks are some subtle, interesting things that could be improved in language. It's a really good talk, very self-deprecating, very good. I think the most important thing that's hard in Julia is compiler latency. So every time you run a function with a new input type, the compiler runs. So that, in practice, what that means is the first time you call a function, it's slow because you're waiting for the JIT to actually compile it into native code. If you're running the same function lots of times, it really doesn't matter. If you're running the function exactly once in something like a shell script or like an AWS Lambda, it's really awkward. There are tools to sort of work around this, but it's one of the fundamental things that are hard about working in Julia. The workaround is static compilation. So there's a tool called package compiler, which will take your Julia code and turn it into a totally standalone compiled executable. But this isn't a very common workflow yet. You might run into bugs. And the resulting binaries tend to be pretty big because they include a lot of the Julia itself in them. It's also hard to use Julia in an embedded computing context. People have successfully run it on Raspberry Pis, but on smaller systems than that, I think you'd be in trouble. Again, because the language itself has a runtime and a compiler that are going to consume resources that you might need for your code itself. And again, static compilation can help, but you're kind of on the bleeding edge of Julia development there. I think static analysis is another weak point of Julia. There are some linting tools. I haven't really used any. There's one built into the VS Code extension. And I don't really know of any good static analysis tools for Julia. Part of it is just that the language is new. I think it's also harder because it's dynamically typed. Although I would point out that static analysis of C++ is not only hard, it's actually literally undecidable in general, but we still have tools that do a pretty good job. So I'm kind of hopeful that we can do better than the current state of the art with Julia, but it's going to take time. Okay, so any questions about what's hard to do in Julia?
So I have a quick one, Robin. I was looking up pattern matching to see what was available, and the first thing that came up was why pattern matching is difficult in Julia. So at some point, can you just speak on the pattern matching story in Julia?
Yeah, so that was one of the things I really liked about Rust. So I'm far from a Rust expert. I did a little bit of it, and one of the things I liked the most was the really nice way you could sort of pattern match even nested objects. There's no built-in support for that in Julia. So if I'm writing a switch statement, I write a bunch of if and else ifs. There is a macro I'm aware of called, I think it's @match, which has, I think, some of the basic features, but it's hard. Yeah, this is not something that's built into the language. I think the best thing I can say is that the fact that the meta programming tools, so macros in Julia, are so good, so much easier to work with than in a language like C. A lot of things that would have to be built into the language in another language don't have to in Julia, because you can actually implement, using macros, you can implement new syntax.
Right, which is what I figured, and that's kind of when I started reading in there. They're talking about some packages, right, that do it,
right,
and that people found really useful. So
yeah, exactly. I mean, one thing is that it's often annoying that struct foo, you might want to provide default values for these entries. The Julia language doesn't support this natively. You can create a constructor with defaults, but it's really nice to just be able to write them in line, kind of like you would in C++. Well, people noticed that was kind of annoying, and so there's a macro called is it kwdef. I don't have the package added right here, but it's keyword def. So you add this macro, and it turns this what was formerly invalid syntax into totally valid, meaningful syntax. And so we don't have to change the language. We don't have to do anything. You can implement that in a package and create the syntax that you want. And in fact, this one proved to be so useful that it actually did get added to Julia base, just because it was so nice.
Oh, nice. Excellent.
Cool. I gotta say though, Mike, I was thinking when he was showing that greet earlier with the multiple dispatch, that looked a heck of a lot like pattern matching to me.
So it's I think it's parametric polymorphism. I always get that mixed up with other things, but essentially, so that part of it, right, is extremely nice, right? But other things like Robin had mentioned, like the switch, right, or just like trapping values, kind of having them fall through. But with macros, it seems like there's enough tools that you're able to get the job done. So, cool. Thanks, Robin. That was a great answer, and I appreciate you going in there, especially with that example that you just gave with the keyword def. That's pretty neat because, again, right, like I'm so used to defining structures with default values, right? That'd be like one of the first things that I would do, right?
Right,
So,
it's really nice, I see a question from Carlos about Julia for website apps. So I've done a little bit of that. I actually have one Julia package hosted as a web app on AWS. It works fine. There's a tool called http.jl, which is for sort of the basics of interacting with web requests, which I actually showed earlier in the talk. And there's a tool called Mux, which is a very simple web server. I'm not an expert on sort of large scale web programming at all. It's just not something I do. I think in general, it's not an area that there's a lot of work being done in the Julia ecosystem. There are people who care a lot about it, but probably thousands of times more people are doing this in Python right now. I think the language itself is very well suited, right? The fact that we have good asynchronous primitives and multi-threading primitives makes it a good choice. It's just not something people have done a lot of. And you were also asking about literate programming. Yeah, so Jupyter, I think, is great for it. This is that, right? I am embedding code in a slideshow while I'm doing this, and we could render this to a PDF as well. There's a tool called weave.jl and another one called literate.jl, which do very much the same thing. So you can write code in a text file and then generate that as, for example, a PDF, which will embed all of the graphs or images or whatever output that code produces. Okay, so I'm basically at the end of my time, but I want to just give you some pointers to useful Julia tools, and then I'll leave up the last slide, which has sort of where to go to learn more. If you're an IDE person, the Juno is the most full-featured IDE in Julia. It's built on top of Atom. It has things like the debugger and profiler support, although you can use those without the IDE if you want. Evaluation of expressions, docstring lookups, sort of the basic things you would expect. If you're more of a VS Code person, there's Julia VS Code, which has similar support. I think it doesn't have an integrated debugger, but it does have a really nice viewer for plots and tables, and it hooks into the general Visual Studio Code language server, which is really nice. I actually use Julia mostly through Sublime and Jupyter, which also works great. Flux is I think the best known and most stable machine learning tool in Julia. I put it here because this is one of the tools that I used to get my actual PhD, because I did all of my PhD work in Julia, and Flux was integral in actually making that work. I think the really nice thing about it is that it's extremely general. It's written all in Julia, and so it's very easy to look at a model and inspect, oh, how does this actually work? You can use which, figure out what does this function call. You can change anything you want inside the whole package, create new behaviors, create new kinds of machine learning algorithms. Differentialequations.jl, another package instrumental in me actually getting my PhD, has solutions to sort of every kind of differential equation I've ever heard of, and then a bunch more, including neat features like automatic differentiation. It works on GPUs. It even computes sensitivities and has access to every solver I've ever heard of, and a bunch of new Julia ones that I hadn't heard of. This is actually how we simulated our robots. So we set up our robot as a differential equation and then simulated that differential equation using this package. Data frames, another tool I needed for my PhD. It's very similar to pandas in Python. Definitely not as mature, but it's growing really quickly, and it's improved a lot in the last few years. So just good support for tabular data in memory, the things you might expect, like joining, indexing, grouping, etc. There are also tools for out-of-memory tabular data, but I have no experience with them, but I can point you in the right direction if you're interested. Jump is one of my favorite Julia packages. It's a tool for optimization. So setting up optimization problems where you don't know the answer, but you know something about the constraints. You know what a good answer might look like, and you want the computer to go find it for you. It's really the same problem as machine learning, just done on sort of a different scale. And so I actually, again, used it to get my PhD. It has the support for a variety of solvers, continuous and discrete optimizations, which if you're the kind of person like me who cares about that, that's really important. And it sort of creates, essentially using Julia macros, its own domain-specific language. So a way to write down optimizations that's easy to read and easy to extend. And this is just an example of solving a problem of navigating this robot back to its home at the center of the grid, which I solved with a sequence of optimization problems in Jump. And actually, if you go to the slides that I linked, you can see the source code for this, where I set up that optimization in Julia. In the really esoteric, weird stuff, I think cassette is sort of the weirdest cool thing you can do in Julia. Cassette allows you to do something that would be difficult or impossible to do in most other languages. So it actually allows you to sort of hook into the compiler itself. So you can create a context, and within that context, modify the behavior of existing functions without redefining them. So one of the things you might want to do is, given a function that computes a value, instead compute its derivative. And so cassette is a building block for a way to, say, take a function and transform all the functions that it calls so that instead of computing values, they compute derivatives. And do that in a way that's really easy to extend and that offers really good performance. So you're not adding a bunch of if statements everywhere throughout your code. You create something that can compile down to a very efficient code, but done in this really nice composable way. It's complicated. I've used it a little bit. It gets into the deep, dark Julia compiler magic. And if you're into that, it's definitely worth checking out. Okay, so that's all I have. But I want to leave this up because I think it's a good summary of where to go next. So if you're interested in Julia and you want to learn more, obviously the best thing to do is just download it and start playing with it, just like any other tool. So that's julialang.org. The manual is great. I think it's very readable. You can just sort of sit down and look through that. If you want to take a course instead, Julia Academy, which is, they're run by Julia Computing, which is an organization that helps promote, they're the corporate side of Julia. They don't own the language, but they employ some of the people who wrote the language. You can also ask questions on Discourse and on Slack. You can find me on Discourse. And Julia Hub is a great list of all of the packages that are registered in Julia, of which there are several thousand, including useful pointers for related packages. And with that, I'll happily take any other questions you guys might have.
So, Robin, you said static compilation is something that they're just now trying to get to. So what does it compile down to? Does it compile to like an intermediate representation that the LLVM uses, or?
It compiles down to a native shared library. So
okay.
The Julia compiler, I mean, you're still right. Like the Julia compiler produces LLVM's intermediate representation, and then LLVM turns that into native code. You as the user never have to care about this. And so the package compiler, it produces a static shared library. The difficulty is just that shared library might include part of the Julia runtime itself in order to actually run your code. And so that can result in it being kind of big. But this is the kind of thing that it's been known for as a sticking point, and I've encouraged that it's improved a lot. So the biggest priority of the compiler developers team in the last year or so has been improving the latency. So how long does it take to go from a cold start to something like a working graph? And they made really big strides. I think it's come down by like a factor of 4 in the last 6 months, which is really exciting. But there's still a long way to go. I mean, if your job is something that might just be, do a bunch of simple operations in a shell script, like right now, I think Python is still a better choice.
Well, actually, I'm thinking about like if I say, okay, let's say I build an executable and I want to give it to users. Do I have to give them the Julia runtime or Julia in order for them to run it? And that's what I'm thinking of.
Got it. Yeah. So no, if you use package compiler, you can create a standalone executable that they can run without installing anything else.
Got it.
Yeah, and that totally works. Really, just the downside is that because it's not a very common workflow, finding documentation for it can be more challenging. Finding people who are experts in it can be more challenging. But yeah, it absolutely can be done.
That just reminded me of something too. So I know a lot of these newer languages, it seems like they might have a little bit of difficulty, with compilation on Windows versus Mac versus Linux or whatnot. How is that with Julia? Is it pretty easy to kind of get started and start playing around with all three? And
great, it's so much better than anything else. Yeah, I mean, if you're running code that is written entirely in Julia, you'll never notice that you're running on a different platform. It should be exactly.
Oh, nice.
And where things can get more difficult is if you're calling a Julia package that calls a Julia package that calls a Julia package that somewhere is calling actually into a C library. Somebody has to compile that.
Right. Yeah. No, that makes sense.
So the good news is that actually the Julia package manager just recently sort of learned how to support assets. And so it's now gotten a lot easier to statically compile ahead of time. It's like cross compile a binary that you might need, and then ship that with the package so that other people, someone might download your package on Windows, and in the background, it's actually downloading the compiled asset for some C library that you're depending on, and they don't have to care. They don't have to have installed a compiler.
That's really smart. Yeah.
Compared to,
nice.
I've at work, I professionally occasionally have to support C++ compilation on Windows, and I hate it. And I've done Python installation on Windows, and it's kind of annoying. And Julia, it pretty much just works.
Okay, cool. One other quick one I had was with testing, is there kind of a canonical answer to testing in Julia, or are there some competing things?
So
I heard
There's a
something
built-in
about
package
doc
called
test earlier, which is
Yeah.
pretty cool.
There's a built-in package called test. It provides a macro called @test. We can do @test set. And we can group tests into tests. And oh, by the way, one of those tests has failed. And it's showing us slightly off the screen, but it's showing which test failed, what the expression was, and what it was instead. So the built-in test, it's pretty basic, right? It doesn't have support for things like mocking or other test fixtures. I have found in Julia that that's less necessary, although that might just be confirmation bias because it's not there. But I think that the focus on sort of an explicit separation of nouns and verbs, types and functions, rather than organizing everything into giant classes, tends to encourage me to write code that's a little bit easier to test, because I tend to write functions that take fairly specific input and produce fairly specific output. But I can't say that with much certainty.
Yeah, pure functions are always easier to test.
Yeah, exactly.
Definitely. 100%.
The fact that that's very easy to do in Julia and is sort of encouraged by the language itself helps at least nudge you in the right direction.
Cool. Anyone else have questions for Robin?
Well, today I learned that Jupyter Notebook can be doing work with something other than Python and can be used as a slide deck.
Yes, it's great.
The first thing I did was look up Jupyter for Julia because I thought that's what you might be using or something like it. And sure enough, I was like, what? Like, cool.
Yeah,
That's awesome,
in fact,
man.
I'm using a plugin
That's
called
freaking awesome.
I think it's in Python, it would be pip install this one. So this is it lets you create Jupyter slideshows that are then interactive. So by default, Jupyter exports the slides, but they're static. But I really like being able to, play around with the slides while I'm presenting them, which is terrifying and dangerous. But, but yeah, so Rise is an extension that I really like for that. Well, that's what I'm using right now.
Best way to find out what you don't know is live code in front of other people.
Boy, yeah, isn't it? Okay, there's a question on how does garbage collection affect real-time performances in robotics? Yeah, so that's a super good question. There's not a clear, well-defined answer on that right now. And actually, that was one of the things that I brought up in my last JuliaCon talk about robotics, was sort of, this is kind of an unknown area. I think the best answer we have right now is, if you really care about real-time performance, and this is, I think, true whether or not there's a garbage collector, the best thing to do is don't allocate memory. And the good news is in Julia, that's actually pretty easy to do because it's easy and common to write functions that operate in place. So you pass in a workspace or you pass in a result that you want to be filled. But yeah, it's true. So if you really care about things like sub-millisecond garbage collection pause times, the Julia garbage collector doesn't have that yet. I know that Java has done a lot of work on creating deterministic, and I think Go as well, deterministic low latency garbage collection. And it's just not the sort of thing that enough effort has been put into in Julia yet. I would say right now, with the state of the language as is, I would still be comfortable writing a robot controller in Julia, and we've done that, and just by avoiding memory allocation. But the situation is definitely not perfect.
That reminded me of a question I do want to ask. In terms of garbage collection, you said nothing is copied. Everything's shared, right? So when you get to garbage collection, does it have to do like a stop the world situation?
Yes.
Okay. So that makes sense. Okay.
Yeah. And so I should be more careful that nothing is copied as far as you can observe. If you have an immutable data type, the compiler is free to copy that wherever it wants, and it will do so to make the code more efficient because it's immutable. If you can't observe the fact that there's copying, then as far as you know, there is no copying.
Gotcha.
And so in practice, what that means is, for example, this point type, I can create those essentially for free. These are immutable. They actually live on the stack. So I can, at time, I can benchmark time creating these points. And actually, in this case, the compiler has been very clever, and it's elided that whole operation. So it's taking less than one clock cycle. And what that really means is the compiler figured out that this doesn't do anything. It's just skipped it. But it also means it allocated no memory at all. And so creating these, these lightweight data structures is essentially totally free. It doesn't allocate any memory. It doesn't introduce any garbage collection penalties. And we rely on this very heavily in the Julia robotics world. So there's a package called static arrays, which lets you create essentially the generalization of this point type to arbitrary numbers of dimensions and arbitrary element types. So we can create, a collection of 3 vectors, and we can create more of them and throw them away and build them for move them around. And there's no garbage collection issue. There's no allocation cost there.
Would it be possible to turn on a feature in a linter, for instance, to give you warnings saying, you're allocating and you said you wish not to?
Yeah, I think it would be challenging to do that in a linter, but I think it would actually not be too hard to do that in a language extension. So to create a macro that would do something like that. And I actually talked to Jeff Bezinson the last time I gave a JuliaCon talk about this. And he said he would look into it, and I want to bother him again because it hasn't happened yet. So yeah, I think you could do it in a linter. I think one of the challenges is, looking at a call of f of, there's no way to look at this function on its own and know whether it's allocating any memory. So you have to be looking inside the definition of f and then figuring out, recursively for all of those function definitions. But you can look at, fairly common cases. So if you have an array x and an array y, and you do x plus y, well, that's going to allocate a new array for the result.
Right. Most IDEs build an internal model of the things that you're doing. So it goes beyond being a linter.
Yeah. Yeah, I agree. I mean, and I think things like the IntelliSense in Visual Studio are really good at this. And some of those tools exist in Julia, but it's not nearly as mature as in languages that have been around for much longer.
So Norio,
if no one else has any other questions, or before I go ahead and ask your questions, I want to say this before I forget. First of all, thank you so much, Robin. It was a terrific presentation. That really scratched my itch to know more about Julia.
Awesome.
And also, Robin I kind of put out a general message on the Julia discourse board, and Robin very kindly offered to come and help us right away. And so I really appreciate that, because I really don't know very many people in the Julia community, so that's really nice. And just wanted to say big thank you for this.
Absolutely. I totally agree. Yeah, this has been a really, really interesting talk. I mean, I feel like Julia has a lot of the really nice little tools, right? That a lot of languages maybe have a few of them or whatever. And I'm like you said, I appreciate that you threw out the rough spots, right?
Yeah.
So that you're not trying to sell us the the snake oil, but I'll tell you what, I'm pretty impressed, and I've got to find something to play around with this language. So thank you.
That's what I'm thinking too, Mike. It's like, man, what can I do with this?
Normally I'm like, I'm too busy, but I have to try something with this, even if it's just messing around with the Jupyter notebook stuff, because this is pretty sweet, man.
I would definitely start. I think playing around in Jupyter is a really nice way to just sort of get a sense of the language and get some instant gratification.
Yeah, definitely.
I'm relieved to discover that I wasn't completely losing my mind, but I had 2 names mixed up, because Honorio, you put on had a speaker talking about Rosie, which I had conflated with Julia, and I thought, what do you mean it's not a pattern matching language?
That is funny.
Sorry about that, Bob. And we'll probably try and get Jamie here sometime to talk about Rosie again. She's been doing some stuff with it. But yeah, it unfortunately, Rosie is a terrific tool, but it's kind of a very, it's really kind of a glorified DSL in that sense, So, but yeah, I can understand the confusion there for a second.
Cool. Do we have any other questions for Robin?
Okay, and 2, again, before I forget, I apologize, I'm repeating myself, but I want to make sure everybody hears, because otherwise they may not remember this. Next month, Bruce Tate, author of 7 Languages in 7 Weeks, is going to be talking to us. Like I say, I don't remember the topic right now, but I can guarantee it'll be interesting. So definitely please join us next month. And it's probably gonna be remote again, even if they, decide to lift all the stay-at-home orders and everything. Probably still gonna do it remote, so we can, get more people on.
Absolutely, and we'll be announcing that really soon. I'm also going to post the GitHub stuff, Robin, that you posted,
Perfect,
basically
yeah.
going through. Super great to be able to follow along. But I'm going to post that on the meetup. I'm going to post it also on our Twitter. So wherever you found this meetup, essentially, you should see that posted tonight. So I'll get that on there for everyone.
All right. Thanks
And
a
if
lot.
anybody missed it, Robin just nicely posted on the group chat how to get a hold of him on discourse.julialang.org if you need to. So,
Perfect.
if anybody wasn't aware of that.
Awesome. Well, hey, thanks, Robin. Appreciate you, coming out and speaking for us, and
Yeah.
really glad to see some new faces in here too. Awesome to see people probably across the world. Who knows? But it's great to see everyone. And Altimetric, just want to thank both of you for hosting again and being here for us to support the group.
Yes,
So really
thank you,
looking.
Ryan and Jacob both.
Yep.